Imagine, just imagine slipping on a pair of regular, completely normal-looking glasses.
Right, like no bulky visors.
Exactly. You don't have to adjust heavy head straps or anything. And the second they rest on your nose, a full-color, high-resolution virtual world overlays perfectly into your field of vision.
And no color bleeding either.
Yeah, no chromatic blur causing eye strain. It's just a flawless optical integration that feels as natural as, looking through a window. That compact, artifact-free experience is basically the holy grail of near-eye displays.
But getting the physics of light to actually cooperate with a form factor that small, I mean, that has been a massive hurdle for optical engineers.
Oh, absolutely.
Because you can't simply shrink traditional curved glass lenses down to the millimeter scale without introducing severe optical aberrations, especially when you're dealing with the entire visible light spectrum.
Well, welcome to the 2PP podcast, and welcome to this deep dive. Since you listening right now are already deep into the world of two-photon lithography, you already understand the sub-wavelength precision of TPL.
Yeah, you know exactly what the hardware can do.
Right. But today's mission focuses on a completely novel application that pushes the boundaries of that precision. We are unpacking a recent Nature Communications paper where researchers built a 3D RGB achromatic metalens.
Which is huge.
It is. They essentially bypassed the historical limitations of flat metasurfaces to make that compact VR dream possible. And more importantly, they solved the scalability bottleneck of 2PP to actually mass produce it.
Yeah, because the researchers didn't just design a single clever optical element here. They engineered an entire end-to-end manufacturing framework.
Right, from start to finish.
Exactly. We're looking at a system that combines a discrete 3D meta-atom library paired with a differentiable inverse design algorithm. And that's topped off with a nano-armoring technique that finally allows two-photon polymerized structures to be reliably replicated using nanoimprint lithography.
So to really grasp the magnitude of what they've pulled off, we need to trace this back to why conventional 2D flat optics have just consistently failed to deliver that perfect full-color VR experience.
Yeah.
Like, we've all seen impressive flat metalenses before, but they constantly struggle to focus white light accurately.
Right, and it basically boils down to the mechanics of the propagation phase in standard polarization-independent metalenses.
Okay, let's unpack that.
So in a conventional flat metalens, you modulate the phase of incoming light by altering the diameter of millions of tiny nanopillars spread across the surface. But because traditional lithography techniques are inherently planar, every single pillar across the entire lens is restricted to the exact same fixed height.
So the engineers only have a single knob to turn.
Right.
They can change how wide the pillar is, but the vertical distance the light travels through the material is permanently locked, like trying to play a complex chord on a guitar with only one string.
That's a great analogy.
Yeah.
And that creates a massive physical limitation when you want to control multiple wavelengths simultaneously.
Because different colors act differently.
Exactly. Light at a 450 nanometer blue wavelength interacts with a physical structure very differently than a 635 nanometer red wavelength.
Right, of course.
So if you want a true achromatic response, where red, green, and blue light all focus perfectly at the exact same focal point without chromatic aberration, a single fixed height just doesn't provide enough phase coverage to bend all three colors to the same degree.
And to compensate for that structural limitation, researchers usually have to rely on exotic high-index materials, right?
Yeah, and they end up designing these wild, highly complex, anisotropic shape.
Like the tiny crosses or the square rings.
Exactly. Instead of simple pillars, you see patterns that look like intricate little mazes, just trying to force the different wavelengths to align through complex geometry alone.
Which is a nightmare to manufacture.
It's a total crutch. And they are highly sensitive to manufacturing errors. But this is where the researchers in this paper play their trump card. They realized that by utilizing 2PP, they didn't have to be trapped in two dimensions.
They got the whole fretboard.
Right. They introduced height as a second, completely independent degree of freedom. By systematically varying both the diameter and the height of the pillars, they could drop those fragile, complex shapes and the exotic high-index materials entirely.
So what did they use instead?
They just used a standard, low-index, negative photoresist IP-DIP2, and they created a comprehensive library out of simple, solid, cylindrical nanopillars.
Simple cylinders. That's so clean.
Yeah.
Let's look at how they systematically built that library, because the parameters are incredibly precise. They locked the period, the spacing between the center of each pillar at 450 nanometers.
Which prevents optical aliasing and suppresses unwanted diffraction orders across the visible spectrum.
Right. And then, to control the diameter of the pillars, they simply swept the laser power.
Yeah, they started the exposure at 12.5 milliwatts and increased it in 0.5 milliwatt increments, going all the way up to 15.5 milliwatts.
And because of the nonlinear nature of two-photon absorption, increasing the laser power slightly expands the focal volume, or the voxel.
Exactly. Each of those half milliwatt steps reliably broadened the pillar diameter by about 20 nanometers.
That is so cool. So that covers the horizontal axis. For the vertical axis, they just stacked the voxels.
Yep.
They used a slicing distance of 100 nanometers and built these cylinders up to anywhere from 600 to 1,300 nanometers tall.
So you suddenly have a vast matrix of simple cylinders. Some are short and wide, some are tall and skinny.
Right.
And because you have both diameter and height working together, you can dial in the precise phase delay needed for blue, green, and red light using simple physics, rather than relying on those highly complex cross shapes.
I love the elegance of that approach. But this introduces a serious mathematical wall.
Oh yeah, a big one.
If you're independently varying both the diameter and the height of hundreds of thousands of individual nanopillars across a millimeter scale lens, and you need to match the phase for 3 different wavelengths simultaneously, that creates a staggering combinatorial explosion.
It really does.
If you have billions of possible structural arrangements, how do you possibly compute the ideal layout?
Well, a brute force mathematical search over all those combinations for every radial pixel is just mathematically intractable.
Right, a computer would melt.
Exactly. Human intuition cannot navigate a 3D design space of that magnitude, and standard trial and error software would run for years without finding the optimum configuration.
So they couldn't just use off-the-shelf solvers.
No. They had to build a custom, fabrication-aware inverse design algorithm, something that inherently understood the exact physical constraints of their 3D printer.
Okay, so how did they do it?
The first piece of that algorithmic puzzle was establishing a ground truth for how their printed structures actually behave optically. So they ran rigorous coupled wave analysis, or RCWA, to build their meta-atom library.
Let's break down RCWA for a second for anyone who might be a bit rusty, because it's vital to why this works. It's not just a basic retracing simulation.
Far from it. RCWA rigorously solves Maxwell's equations for periodic structures. It calculates the complex transmission, which means it computes both the amplitude of the light passing through and the exact phase delay it experiences. And the researchers ran this intense analysis for every single printable cylinder in their IP-DIP2 matrix against all 3 target wavelengths.
So they essentially built a massive lookup table. The algorithm knew exactly how a 900 nanometer tall, 200 nanometer wide pillar would bend red light versus blue light.
Exactly.
But a database alone doesn't solve the combinatorial explosion. You still have to choose the right combination of pillars for the entire lens.
Right. To tackle the selection process, they broke it into 2 distinct steps. Step 1 was ring-wise phase preselection.
Okay, how does that work?
They started with their ideal mathematical target, the hyperbolic phase profile that perfectly focuses light. For every concentric ring extending out from the center of the lens, they checked their RCWA database and calculated the RGB phase error for every single candidate pillar.
Oh, so they were filtering out the garbage. They looked at a ring and evaluated which of the cylinders got them mathematically closest to the target phase for red, green, and blue simultaneously.
Yeah, and they just threw away anything that didn't make the top cut. They aggressively shrank the search space by keeping only the top K matches for each radial ring. But that still leaves a complex optimization problem.
Right, because the optical performance of one ring affects the focusing efficiency of the whole lens.
Exactly. You still have to find the absolute best holistic combination.
Which brings us to the second step, differentiable discrete selection. And here's where it gets really interesting to me. Standard machine learning relies on gradient descent, which requires continuous variables to calculate the slope of the error.
Right.
So a standard machine learning algorithm wants to suggest something like, the math works best if we use pillar option 3.7.
But the physical 3D printer cannot fabricate a fraction of a blueprint. You either print design option 3 or you print design option 4.
Exactly. The algorithm has to output discrete whole numbers to be viable for manufacturing.
And to bridge that gap between continuous math and discrete manufacturing, They parameterized the choices using learnable logics and applied a hard Gumbel softmax with a straight-through estimator.
A straight-through estimator STE. I think of it like an advanced sorting hat, or like an industrial switchboard.
That's a good way to look at it.
Right, because during the forward pass, when the algorithm is deciding what to physically print to test the simulation, the switchboard mathematically forces the system to pull one distinct lever. It strictly selects one physical, printable pillar per ring.
However, during the backward pass, when the algorithm is evaluating its optical mistakes and updating its internal weights, it bypasses that hard physical switch.
Oh, wow.
Yeah, the straight-through estimator allows the learning gradient to flow backward through all the structural options as if the choices were continuous.
That is brilliant.
It tricks the neural network into smoothly learning, which discrete physical pillars work best together across the entire surface of the lens.
It marries the continuous optimization power of machine learning with the discrete reality of lithography. And they guided this whole learning process using a minimax wave optical performance metric based on the angular spectrum method, right?
Yes. The angular spectrum method, or ASM, allows the simulation to accurately propagate the complex wave field from the surface of the lens all the way to the focal plane.
And what's the minimax part?
Well, by using a minimax objective, the algorithm wasn't just trying to maximize average efficiency across the board. It specifically analyzed the worst performing wavelength of the three red, green, or blue and mathematically fought to maximize that specific color's efficiency.
So it optimized for the worst case scenario to guarantee a balanced output.
Exactly. And the theoretical outcome reflects that focus. The simulation produced a focusing efficiency of 33% at 450 nanometers, 34% at 532 nanometers, and 34% at 635 nanometers.
Those numbers are incredibly flat across the spectrum. That lack of variance is exactly what proves the true achromatic nature of the design.
Yeah, it's remarkably consistent.
But let me push back on the physical reality of fabricating this. A perfectly balanced digital blueprint is a fantastic academic achievement. But we all know two-photon polymerization prints voxel by voxel. Now, I know the industry is currently riding this incredible 20-year exponential trend where 2pp printing speed essentially doubles every year.
It's insane how fast it's gotten.
Yeah, we're printing volumes vastly faster today than we were a decade ago. But even with that exponential speed up, printing a millimeter-scale lens with this density point by point takes real time.
It does.
So if you're trying to manufacture thousands of commercial VR headsets, you cannot spend significant time serially printing individual lenses. How does a framework this precise ever scale up for commercial manufacturing?
Well, what's fascinating here is that the researchers were fully aware of that fundamental throughput bottleneck. They understood that 2pp, despite its massive speed advancements, shouldn't be the final assembly line for consumer products.
Okay.
It should be the tool room. They use the TPL process strictly to create a singular, perfect master mold.
Which opens up a completely new physics problem. If you're using this 2pp print as a master stamp, you eventually have to peel the mold off the master. And we just talked about these polymer pillars being up to 1,300 nanometers tall and incredibly dense. IPDIP2 is a great photoresist, but it's fundamentally a brittle polymer. Wouldn't those high aspect ratio structures just shear right off the glass substrate the second you apply the mechanical pulling force of demolding?
They absolutely would. In fact, the paper details this exact failure mechanism. When the team tried directly casting a soft mold over the bare as-printed IP-DIP2 structures, they witnessed catastrophic structural failure.
I can imagine.
The physical pulling force and the surface tension of the demolding process easily overcame the adhesion of the polymer pillars to the substrate. The structures just rip right off.
So you need the sub-wavelength precision of the polymer to create the optical shape, but you need the mechanical durability of an industrial die to stamp it.
Exactly. And to resolve this materials conflict, they engineered a conformal silicon dioxide SiO2 atomic protection layer. They deposited this directly over the printed metalens.
They applied plasma-enhanced atomic layer deposition, or peeled. But deploying peeled on delicate polymers requires extreme thermal precision.
It's very tricky.
Standard atomic layer deposition often runs at high temperatures, which would immediately warp or melt the nanoscale IPDIP2 pillars, completely destroying the optical phase profile.
So they had to strictly control the thermal envelope, dropping the processing temperature to exactly 60 degrees Celsius.
Wow, that low.
Yeah, and the mechanics of ALD at this scale are fascinating. It doesn't just spray a coating over the surface, it uses alternating pulses of precursor gases that chemically react with the exposed surfaces, building the SiO2 layer literally one atomic level at a time.
At a rate of 1.33 angstroms per cycle. We're talking about fractions of a nanometer, so it's not just draping a blanket over the lens, it's actively forcing a chemical reaction to build a microscopic atomic exoskeleton that perfectly hugs every contour of the pillars.
And that atomic exoskeleton mechanically reinforced the polymer structures and firmly anchored their bases to the fused silica substrate without altering the intended geometry.
That's incredible.
Once this IO2 armor was in place, they successfully poured an HPDMS soft mold over it.
Let's clarify HPDMS for a second. That's hard polydimethylsiloxane. It's a silicone elastomer. It goes on as a liquid, conforms perfectly to the nanoscale gaps between the armored pillars, and then cures into a flexible solid.
Exactly. And when they peeled that cured HPDMS mold away from the IO2 armored master, not a single pillar broke.
No way.
The master print survived completely intact, which meant they could take that soft mold and move to nanoimprint lithography, or NIL. They used the soft mold as a stamp, pressing it into a UV curable resin to mass-produce replicas.
And they were incredibly deliberate with their materials during the stamping process, too.
Right.
They formulated a specific UV curable resin with a refractive index of 1.53.
Right.
Because the original IP2 polymer used in the RCWA simulation has an index of around 1.55, they matched the optical properties almost perfectly, ensuring the replicas would bend light exactly the way the algorithm predicted.
Yeah, the material matching was crucial.
But my immediate skepticism is about the fidelity of the transfer. You take a pristine 2pp print, add a layer of atomic silicon dioxide, cast a silicone mold over it, and then stamp that into a new liquid resin. Does adding this atomic armor and using a stamped resin alter the optical perfection we achieved in the simulation?
Well, the microscopy data answers that definitively. When they put the stamped resin replicas under a scanning electron microscope and compared them to the original master, there was no significant dimensional deviation.
Really?
The structural transfer was essentially flawless. Furthermore, to prove industrial viability, they ran 10 continuous replication cycles using the exact same HPDMS soft mold.
10 full stampings with no degradation.
Zero noticeable degradation to the morphology of the mold or the resulting lenses. It effectively bridges high-performance 3D metasurfaces with scalable, high-throughput manufacturing.
Okay, so with the mass production bottleneck solved, the final step was proving the lens could actually function in the real-world application that started this whole pursuit, a near-eye VR display.
Yeah, the moment of truth.
They took one of the printed replicated metalenses, which measured 1.89 millimeters in diameter, and put it on the optical bench. The experimental results yielded a focal length of 4.5 millimeters and a numerical aperture of 0.21.
And the measured focusing efficiencies also validated the Minimax design. They hit 27.1% for blue, 28.2% for green, and 29.1% for red.
Those experimental numbers are slightly lower than the theoretical 34% from the simulation, which is completely expected due to minor fabrication tolerances. But the critical part is that they remain incredibly balanced across the RGB spectrum.
Very balanced.
But for me, the undeniable proof of quality lies in the Strehl ratios. They measured 0.90, 0.89, and 0.93.
Yeah, for anyone needing a quick refresher on the optics side, the Strehl ratio is a standard measure of optical quality. It compares the peak focal intensity of your actual manufactured lens against the theoretical maximum of a mathematically perfect lens without aberrations.
Right. A ratio of 1.0 is absolute perfection. And the general consensus in optical engineering is that anything above 0.8 is considered diffraction limited.
Yeah.
It means the lens is essentially performing as perfectly as the fundamental physics of light will allow. Hitting around 0.90 across all three colors is a monumental achievement for a printed metasurface.
It really is. And to visualize this performance, they integrated the 1.89 millimeter Metalens directly with an OLED display panel. This panel had a pixel pitch of 7.2 micrometers. They projected light through the lens and captured the output on a CMOS sensor, basically mimicking what the human retina would perceive.
And they didn't just project colored dots. They displayed complex, full-color images, including a 3D rendering of a white rabbit and a university logo. Now, if you attempt this with a standard aberrated lens, one suffering from chromatic aberration, You get a miserable visual
Oh,
experience.
terrible, because different wavelengths of light refract at slightly different angles when passing through the same material. Blue light bends more aggressively than red light.
Which means the blue part of the image focuses at a shorter distance than the red part. To the user's eye, this creates a severe ghosting effect.
Right.
The blue edges look blurry and slightly larger, peeling away from the red and green channels. You physically cannot render pure, crisp white light because the spectrum constantly separates.
However, because this 3D Metalens utilize the height of the pillars to perfectly match the phase delays for blue, green, and red, all three wavelengths converged onto the exact same image plane simultaneously.
The images captured on the CMOS sensor showed stunning, crisp, broadband, white light imaging. The rabbit looked perfectly sharp, with zero color fringing at the edges. So what does this all mean for the end user?
If we connect this to the bigger picture, this fundamentally changes VR hardware architecture. A traditional VR headset requires empty physical space between the display screen and the refractive lenses to give the light room to focus properly.
And that focal length requirement is the sole reason VR headsets stick out 3 inches from your face and drag your head forward.
It's exactly. This achromatic Metalens collapses that necessary distance. It allows engineers to position the display panel incredibly close to the eye while maintaining a flawless, full-color image. It compresses a bulky optical train down to the millimeter scale.
It is just a phenomenal demonstration of end-to-end engineering. They isolated the core limitation of standard flat optics, the 2D propagation phase. They leveraged the unique voxel stacking capabilities of 2pp to unlock the z-axis.
Yeah.
They tamed the resulting combinatorial explosion using an ingenious Gumbel softmax differentiable algorithm.
Then they conquer the mechanical fragility of the polymer by engineering a low-temperature atomic exoskeleton of SiO2, turning a delicate print into a durable industrial mold.
And finally proved that nanoimprint replicas deliver diffraction-limited full-color VR imaging. It's brilliant. But before we wrap up, there is an underlying implication here that I think is wildly provocative for the future of this field.
Oh, what's that?
This entire paper validated the framework using a relatively simple, low-index polymer, IPDIP2. What happens if we take this exact same 3D inverse design and armoring pipeline and start applying it to particle-embedded resins?
Oh, that is a staggering thought.
Mm-hmm.
If you formulate resins loaded with titanium dioxide nanoparticles for the visible spectrum, you could dramatically boost the refractive index and push the focusing efficiencies far beyond 30%.
Exactly. Or use zirconium dioxide embedded resins to manipulate the ultraviolet spectrum. You could computationally design a wildly complex, multifunctional, volumetric optical element.
And with the speed improvements we talked about.
Right. Use the 2pp speedup trend to print the master in an hour, armor it with peeled, and then stamp out millions of highly advanced meta-optical computers in seconds.
It signals a profound shift. The two-dimensional constraint on metasurfaces is effectively dead. The vertical axis is fully in play.
Which means those completely normal-looking, lightweight VR glasses we imagined at the very beginning, the blueprint for them isn't science fiction anymore. It is actively being rendered in voxel data right now. Thank you for tuning in to this 2PP Deep Dive. We always love unpacking the absolute frontiers of lithography with you. Until next time, keep questioning the dimensions of what's possible.